Hello friends, welcome to Einstein. So we have seen that delta t prime equals delta t into 1 minus v square upon c square in the time dilation formula. So the quantity in this, if you closely observe this formula, then you will find that the quantity inside the root should be 1 minus v square upon c square. This quantity must be greater than or equal to 0, because there is no meaning if you say that this quantity is negative, it will give you imaginary roots, so imaginary values. So this implies that this v minus c, this must be less than 1, or we can say that this v must be less than c. So what we get from this time dilation formula is that the maximum velocity with which anyone can travel or any frame can move is the velocity of light. You cannot move, even if you move with the velocity of light, then this quantity becomes 0. That means the frame in which you are moving, no time will be elapsing. All clocks will measure 0 time interval. So this is a constant on the speed with which any particle, a body or any frame can move. So this is the ultimate speed with which anyone can move. So now if this speed is the maximum achievable speed from the time dilation formula or from relativity theory, then what if is this velocity c is constant, or it depends on something? So we know that we will always move with a velocity less than c, but is this c constant? Does this c depend on anything? So is this a speed of light c is constant for everyone, or it depends on the frame in which the observer is moving? And from the last lecture you know that Einstein says that the speed of light is same for all the observers in all directions. So for all observers this speed is same. So is there any possibility of any absolute reference frame? And the question is that how Einstein arrived on this conclusion that this speed is constant, it doesn't depend on any observer. And I said in the last lecture that Einstein guessed this from the electrodynamics. That is, by understanding the Maxwell equations, Einstein was able to tell that the speed of light must be constant for all observers, and special relativity must be a requirement for all the Maxwell equations to retain their form in moving frames. So in today's lecture we will see how from Maxwell equations Einstein was able to deduce that the speed of light is constant for all observers. So let's see this. So before Maxwell, people like Coulomb, Gauss, Ampere, Faraday, Henry Joseph, these people formulated the mainframe of electrodynamics, and they showed how the quantities of in any electromagnetic system behave. So the first thing, the oldest one is the Coulomb's law. You know that Coulomb's law. So we have the forces between two particles is given by F12 equals 1 upon 4 pi epsilon naught Q1 Q2 upon R square. This is the simplest way of writing Coulomb's law. And from Coulomb's law we got the Gauss law. Gauss law. So Gauss law is integration of E. This is the net flux coming out of a closed surface equal to charge enclosed by the surface upon epsilon naught. This is Gauss law. Then we have the famous law of electromagnetism, which is no monopoles can exist. So it is written like the total flux of a closed surface, the total magnetic flux is always 0. B dot ds equals 0. So this is the net outward flux and this is the net flux outward. So magnetic lines always make a closed path, and if you make a closed surface like this, then the magnetic lines coming inside will be equal to the lines going out. So the net flux, outward flux through this closed surface must be 0. So these are the two laws. This law is sometimes referred as the Gauss law of magnetism, but there is no name for this law. This law is Gauss law. So the third is, this is the first, second and third is Faraday's law. Faraday's law is given by the EMF produced equals minus d phi upon dt. This minus term is from the Lenge's law. You have already studied in your intermediate courses. So the EMF produced is the rate of change of magnetic flux, where magnetic flux phi b is equal to b dot s, or if it is changing, then you can calculate it like this. Then phi b equals integration of b dot ds, where s is any area. So this is Faraday's law, and the fourth is Ampere's circuital law. Ampere's circuital law. So Ampere's circuital law says that the line integral of magnetic field is equal to mu naught times the current enclosed by that. Suppose that there are currents in the direction, this is I1, this is I2, then you have to imagine a closed curve surrounding these currents, and the dl vector is pointing in this direction. This is your dl vector. So you have to sum the integral, calculate the integral in this path, in this closed path. So we are writing here a closed sign, and the total current I must be equal to I1 plus I2. So these are used to calculate the magnetic field due to coil, solenoidal coil or a toroid. So this was the situation before Maxwell entered in the field of electromagnetism, all these things like Coulomb's law, Gauss law, the Gauss law for magnetism, Faraday's law and Ampere's circuital law were there. But Maxwell tried to write this equation in a different form. So we will see those forms. So if you have any problem in understanding what I have already written in the 4 laws, so for that you can read any book on electromagnetism, an intermediate level book. You can even read the books which are taught in +2 level, intermediate level. So, and we will be continuing from that level in this lecture. So the first is Gauss law. So Gauss law, you know that this is E dot ds. Sometimes you can write it ds or dA. So let's write this as dA, A for area. So E dot dA equals Q upon epsilon naught, where epsilon naught is the permittivity of free space. So sometimes the integral over area is represented by 2 integrals, and for a closed surface you know that you have to write a circle here, make a circle. Okay, so this is Gauss law. Now this is in integral form. We will convert into a differential form. So how we will do that? So we will use Gauss divergence theorem. So let's learn Gauss divergence theorem if you don't know it all. Gauss, I'm just giving a small overview. Gauss divergence theorem. It's a very famous theorem of vector calculus. It says that for any vector field f dot ds, dA better. So over a closed surface, f dot dA, f is any vector field. So in any space, this is equal to the divergence of that field. So this is the divergence, the nebula operator of that field f, and dV, the volume. For volume you need to write 3 integrals here. So here the integration is over the surface area A, which is closed, and this is the integral over a volume. So this is called Gauss divergence theorem, and we will apply this Gauss divergence theorem. So you can see that this term is exactly coming here. So you can write it in this way, as this is equal to del, nebula is pronounced many times as del. So del dot E, and this area terms goes off and you have dV, and this integration is converted into volume integral over some volume. This volume space is around in which this E is existing, the electric field. So now we have to write this Q term in some volume integral. So you can write it like this. This is 1 by epsilon naught times volume integral of the density, charge density, rho dV. So this is the charge density. Its units will be charge per unit volume. So on comparison, you will easily write this as del dot E equals rho upon epsilon naught. So this is our new form. So these two equations are same equation written in different form. So we will write such equations for all the laws. So now come for the second, magnetic monopoles do not exist, and which is written like this: the total magnetic flux is always 0. B dot dA term equals 0. So we will do the same kind of thing here. So we have to convert this in a volume integral. So you have to take the divergence of B. So del dot B, and this dA goes off and volume integral comes, and this must also be 0 because it's constant, so its divergence must be constant. So we have del dot B equals 0. So you have the same equation in differential form. So now we will write the third and the fourth equation in the same manner. So let's see this. One thing you have to keep in mind that while calculating the divergence using the divergence theorem, the vector field F must be a continuously differentiable field in the neighborhood of that volume V. So the third equation, which is the Faraday's law, or sometimes referred as Lenge's law. So this is E equals minus d phi B upon dt. So it says that the EMF induced in a coil is equal to rate of change of the magnetic flux. So we will, this is in differential form, and we will first write it in integral form, and we will also write in a different kind of differential form. So it is the very basic type which we study in intermediate level. So now you know that the EMF is defined as, you know that electric field equals dV upon dr. So you can use this. Sometimes it is written with a negative sign, but there is already one negative sign, so we are writing just dV by dr. So the potential difference or the potential can be calculated by integrating the electric field with respect to the position. So you can write this EMF term as integration of E dot dl, and this is done around a surface, so it is a closed path, so we will write a closed path indication. So the left hand side we have written that it should be E dot dl, a closed integral. Now for the right term we have phi B equals integration of B dot dA. This is the total magnetic flux. So it is over an area, so we are using two integrals here. So now we have to differentiate it. So d by dt of this term, this integral term B dot dA, this should be equal to, we can take this differential inside the integration, so this must be equal to now this B can be a function of position and time both. It can be a time, it can change with respect to position and time also. So this must become a partial derivative, that is del v upon del t, when this term goes inside dot dA. So now we can equate these two terms. So on equating, you will get integration over a closed path E dot dl must be equal to now there is a minus sign, so you have to write here a minus sign. Now you find that this integration is with respect to is on a path, and this integration is on an area. So we will have to either change this to L or this to A. So we will change this dl to area, and for that we will use Stokes theorem. So first we have to understand Stokes theorem. So Stokes theorem says you that a vector field integrated over a closed path, we are taking the line integral, then this is equal to the curl of that field over an area dA. So this is called Stokes theorem. So we will apply this theorem here. So if you apply Stokes theorem, then you will get del cross E, this becomes dA, and you have the term here, same term, minus del B over del T dot product with dA. So now both the integrations are over area, so these two terms must be equal to satisfy this equation. So we can say that del cross E equals minus del B over del T. So this is the Faraday's law written. This is the same thing, same law written in a different form. So this is the new form in which we have written the Faraday's law. So you can say that this is the integral form of the Faraday's law, and it's already the differential form, and we have written this integral, converted this integral form into a new differential form. So this is the Faraday's law. So now we have the fourth and the last, which is the Ampere circuital law. So before Maxwell, Ampere circuital law was there, and it is written as the line integral of magnetic field equals mu naught in times I, where I is the current, which we have already seen. So it is an integral form for a closed path. Now we have to convert this in a differential form. So you can write it as, because it's over a line, so we will write it in the form of curl. So you can write it as del cross B dot dA. Now for this mu naught I term, you can write it as mu naught into integration of J, where J is current density. So current is defined in terms of current density as integral over an area, or current density you can imagine it as current passing per unit area through a cross section, but its actual definition is that I equals J, because if you write J as I upon A, it's not, it may be true in some cases where all the charges are moving in the same direction, but its actual definition is not this. You have to define I as a dot product of the current density vector and the area vector in which you are finding the current. So in this way we can write the value of current, that is J integration over J and D, and it need not be closed integral. So because this is an integration over area, so you have to use two integrations. So now you can write that these two integrations are over an area, so del cross B must be equal to mu naught J. So this is the new form of the Ampere circuital law. So we will write all these laws in a collective form. So let's write these all laws in simultaneously. It's very crucial to know the situation before Maxwell and the situation after Maxwell, and then only you can understand why there was a need for the theory of relativity, so that the laws of electromagnetism should be satisfied. So actually the special theory of relativity was a kind of requirement, a must for the Maxwell laws. Why we are calling Maxwell laws and not laws of electromagnetism? Because before Maxwell there was some kind of error, or it was not complete before Maxwell, and Maxwell was the person who could see that there is some problem in the laws of electromagnetism, and especially the Ampere circuital law, and which he corrected. And after that correction, a new kind of transformation law was required, because if we apply Galilean transformation laws to those equations, then they were not giving the results which were being expected. So we will first write all the equations before Maxwell. So situation of electromagnetism before Maxwell. So now we will not write in its primitive form, but rather how Maxwell wrote it. So first is, which we have already derived, del dot E. The divergence of electric field is equal to charge density upon epsilon naught. The second is the divergence of magnetic field must be 0. The third is the curl of electric field del cross E, the Faraday's law, must be equal to minus del B over del T. And the fourth is Ampere circuital law, is del cross B is equal to mu naught times J. So now we will closely see what seemed Maxwell incorrect in these, especially for this equation. So all the three equations were completely right, only the problem was this equation. So we will see this in two cases or in two ways. So let's see how Maxwell figured out that there is some problem with this equation. So first we will see that how this equation is correct, and then apply the same concept or same type of manipulation in the second equation. So you know that the divergence of the curl of any field is always 0. So we can use this concept in formulating the new law. So we will take the divergence for the third equation. So if you take the divergence for third equation, then the left hand side must give you 0. So del dot del cross E should give you 0. There is no need for any calculation. You can take any vector, take its curl, and then take the divergence of the new vector. It will be always 0. You can keep it as a homework. So now if the left hand side must be 0, so that must be satisfied with the right hand side of the equation. So if you take the divergence of the right hand side term minus del B over del T, so we have to calculate this divergence. So